Hi everyone, I want to make this molecule diastereoselectively. Over on the left, I have a cyclohexene ring. I also have an ether, and I have a couple of carbonyl groups in a 1,4 relationship. So that's a 1,4 diketone. So in my retrosynthesis, I need to pick one of these to start with. Cyclohexene is a classic motif for a Diels-Alder reaction, so I can do some retrosynthesis arrows like this. That will leave me with this diene and a dienophile as part of the other ring. Now, with a disconnection like this, we should check that we get the right regioselectivity and also the stereoselectivity. Firstly, I can check the orbital coefficients. On the diene, there's a large orbital coefficient on the end, which is consistent with the resonance structure. The largest coefficient on the dienophile can be seen to be here as well, using the same logic with a resonance structure. So that's good. These carbons will join together. We'll get the correct regioselectivity for the reaction. In terms of stereochemistry, I'm going to need to draw it in 3D. Now, the ring structure is 6,5 fused, the 5-membered ring causing a bigger steric block on the bottom face. We can describe the approach of a diene as being on the convex face, which is from above. We can just draw a quick sketch, bearing in mind that the 6-membered ring is pretty flat, particularly around the reacting bit, where I can see if I react with the dienophile on the top face, just using these dotted lines, I can then pick the lowest energy transition state, which will be for the diene attacking like this on the right-hand side. That's because the diene is electron-rich and the dienophile is electron-poor, and we can get a secondary orbital stabilization, which lowers the energy of this exo transition state. That type of orbital interaction is sometimes referred to as a pi stack. We can see if we form the bonds on the top face, the two hydrogens on the dienophile will both move downwards, and that will set the stereochemistry we require in the product. But to check what happens near the methoxy group that's on the diene, I'm just going to change my picture slightly. The methoxy group is going back into the plane, and there's a hydrogen coming forwards. So in the product, we can see that we get this stereochemistry labeled with a star. This again is the stereochemistry that we want. Just redrawing the newly formed blue ring there, the two hydrogens on the ring junction will be in a syn relationship, both pointing down as drawn. And then the methoxy-bearing stereocenter will have the methoxy pointing up and the hydrogen pointing down. This is just folding over the ring. One way we could double check this is to try and define that stereocenter as R or S configured. The highest priority group would be the oxygen on that stereocenter. The next highest, well, that's the bridge to the next ring because it's got carbons plus other stuff nearby. Third highest priority, part of the alkene. And fourth highest priority will be the hydrogen. Just putting that on the flat structure too, we can see the priorities looping around like this on the 3D structure. But when we fold it out to put the hydrogen behind the plane, they align this way instead. Both drawings can be used to show that this is the R configuration. Okay, so looking good. The Diels-Alder should work out for us. Going back to my retrosynthesis, well, I think I'm going to deal with the 1,4 diketone next. And because I have a 1,4 relationship between the carbonyls, I'm going to have to use Umpolung chemistry. This is an idea meaning that we're going to have to use the reverse of the natural polarity of one of our functional groups. I think the easiest way to do this will be to cut at the ring junction here and use a carbonyl anion equivalent. This is sometimes referred to as a D1 synthon. But essentially what it means is that we're going to need to use chemistry that behaves like a carbonyl, which is nucleophilic at this carbon, as opposed to electrophilic, which is much more normal. That will take me back to this intermediate with an aldehyde dangling off. And that's because I think a nice way of doing this would be to use a Stetter reaction. If I generate a nucleophilic carbonyl anion here, I can use it to do a conjugate addition intramolecularly. And luckily, the nucleophile will be held on the bottom face, so I should get the cis ring junction. So I'll just draw out the mechanism for this in case it's unfamiliar. So what I'm going to do needs me to start with this thiazolium salt. I'm just going to leave it generic with some R1 and R2 groups, because you can put lots of things in those positions. I should note that you can also do this reaction with a cyanide anion, but it'll be considerably less toxic to do it this way. Firstly, I'm going to treat this with a base. Triethylamine is good enough, because there's an acidic proton, which I've highlighted here. That will give me this ylid type structure, which can act as a nucleophile on the carbonyl. And here I've just transferred the proton to give me a hydroxyl group. Once I've got that intermediate, I have another acidic proton, just highlighted in blue, that the triethylamine can remove. And this then generates me an enamine. Now, enamines love doing Michael addition, and it's dangling right next to an alpha beta unsaturated ketone. So I can draw the nucleophilic attack like this, which will come from the bottom face and form my final carbon-carbon bond. After a few proton transfers, we'll be left with the thiazolium ring right next to a hydroxyl group, which then can collapse down to the carbonyl, kick out the thiazolium ring, and regenerate it as a nucleophile. So actually, we can use this ring as a catalyst. I should note here that the attack on the alpha beta unsaturated carbonyl can occur on either side. In fact, it will occur 50-50 because the black ring I've drawn has a mirror plane down the middle. If we wanted to make this synthesis enantioselective, we'd need to find a way of making one of those sides more favorable to attack. This would be a desymmetrisation of the starter material. If you're interested, there's some work by Rovis in the mid-2000s, which showed that this can be done by clever choice of your R1 and R2 groups on your catalyst, and I'll leave a link to a relevant paper in the description below. But for now, on with the retrosynthesis. I need to make this intermediate aldehyde, and aldehyde's quite a reactive functional group, so I should probably get rid of it in my disconnection and do a functional group interconversion. I'm going to take it to the alcohol, because that just means I need to do a simple oxidation in the forward synthesis. So for example, a Des-Martin oxidation would work well here. A Des-Martin oxidation is where we take an alcohol and we react it with something called Des-Martin periodinane, which has this structure. Now it looks quite complicated. That's iodine in a high oxidation state of 5. The reagent itself is normally just abbreviated to DMP. What happens first is we do a ligand swap on the iodine, in that we're just doing a substitution reaction, displacing one of the acetates with our alcohol substrate. And then next, all we need to do is eliminate this hydrogen. The acetate floating around could do that, for example, like this, and dump 2 electrons on the iodine center. The result of that elimination is oxidation of our substrate, so here giving us the aldehyde. And the byproduct left behind is this iodine species in the +3 oxidation state, which then doesn't participate in the reaction. Dealing with this afterwards in the lab, you would usually do a reductive workup using sodium thiosulfate to this aromatic iodide compound, which is pretty easy to separate from your aldehyde product. In lots of common solvents, that will just precipitate out, so you can filter it off through a plug of silica, for example. And back to the retrosynthesis. I've identified quite an electron-rich ring system here, and I'm going to exploit the symmetry here too, and do a dearomatization disconnection. That disconnection takes me across here to form a CO bond, and it'll take me back to a phenol like this. This is para-cresol, which is cheap and readily available. And also what I'll need is an oxygen nucleophile, which I can just use ethylene glycol, which is used as antifreeze, which is also very available. Now, what reagent do I need to do that step? Well, I need to use hypervalent iodine again, and the reagent I need is this, which has iodine in the +3 oxidation state. This is a very commonly used oxidizing agent. It goes by many names, largely dependent on which side of the Atlantic you're on. Nowadays, it's more common to see this described as PIDA, that's phenyl iodine diacetate, but it's also referred to as BABE, that's bis-acetoxy-iodobenzene. So how does this work? I'll start with my phenol and react it with the electrophilic iodine-free center. As with the Des-Martin oxidation, this is essentially a ligand swap on the iodine, and the substitution will lose acetic acid. What I've essentially done here is added a really good leaving group. The plan would be to reduce the iodine by doing another mechanism, and I can do that by attacking as a nucleophile onto the aromatic ring. Now, this type of mechanism can work at the ortho or the para positions on the benzene ring, but on steric grounds for intermolecular reactions, it's more common to see it working at the para position, where a nucleophile can come in, break aromaticity, form a CO double bond, and then spit out both iodobenzene and an acetate group. So here the iodine is being reduced, and we're losing 2 leaving groups at once. This is really great for an entropic driving force, and I'll get the product that I want. Just as a summary, here's the full forward synthesis. Starting with para-cresol, I'll react with my hypervalent iodine species in the presence of ethylene glycol as a nucleophile. This will dearomatize and give me the electrophilic Michael acceptors. Next, I'll use my Des-Martin oxidation. That's just using Des-Martin periodinane to oxidize up to the aldehyde intermediate. Next, I need to do the Stetter reaction. So I need to use a thiazolium catalyst in this sort of form, in the presence of a mild base to generate the ylid nucleophile. I'll just note in passing here that you can make these thiazolium salts with lots of different R1 and R2 groups. Just by disconnecting first to take off the benzyl group and form the thiazole ring here, I can just react that with benzyl chloride to alkylate on the nitrogen. And the thiazole itself can be made in the usual way by reacting with an alpha halocarbonyl and a thioamide of some sort, something like this. This will cyclize together nicely, matching up the soft centers to react the sulfur in an SN2-like displacement, and matching up the harder centers there to form a carbon-nitrogen bond on the other side. This will then cyclize into aromaticity. Just completing the forward synthesis, after the Stetter reaction, all I need to do is heat up the intermediate with this diene, and I'll get my final product. I hope you found this video useful, perhaps using some disconnections you hadn't seen before. Do let me know your thoughts in the comments below.